Alright, so in this question we have an open top box is to be constructed so that the base is twice as long as it is wide. Its volume is to be 2,400 centimeters cubed. Find the dimensions that will minimize the amount of cardboard required. So our first thing is let's figure out what we want to optimize in this question. Okay, they tell us that we want to minimize the amount of cardboard. So if we're talking about the amount of cardboard that's going to go into making this box, the thing that we want to minimize is the surface area. So that means we have to come up with an equation for the surface area of this box, and we're going to take the derivative, set it equal to 0, and find the minimum value. So I've drawn a little picture of our box over here. I've labeled some variables here: width, length, and height. Those are going to be the dimensions of our box, and I've kind of tried to indicate that it's not going to have a top on it. They tell us that the volume is 2,400 centimeters. So let's come up with an expression here for the volume of this box. It's going to be width times length times height, because it's a rectangular prism. Now, the other piece of information they give us is that the base is twice as long as it is wide. So this length of this base is going to be 2 times the width of the base. So we can make that substitution here in our expression for our volume. It's going to be width. Our length is going to be 2 times the width times height. So this is just going to be 2w squared h. And we know that this volume is equal to that 2,400 centimeters cubed. So we can we're going to be using this expression a little bit later, but let's get on to setting up our equation for the thing that we want to actually minimize, which is our surface area. So our surface area, what do we need to figure out our surface area? I'm just going to add a little bit to this diagram here, sort of fill in those missing dimensions there. We need to have, well, let's see, what parts of our box do we actually have to need to make? We need to make the base. We have the 2 ends, so this end and this end. And we have the front and the back. Let's say the front and the back. Okay, and we want to add up the areas for all of those parts. So let's see, our base is just going to be, well, length times width is a rectangle, so w times 2w, our length times our width. Our ends are both going to be, let's see, they're both width by height, so w times h, and of course we have 2 of them, 1 on each end, so we'll multiply that by 2. And our front and our back both have dimensions 2w times h, but again we have 2 of them, both the front and the back, so we're going to multiply that by 2 as well. So just simplifying this a little bit, we have 2w squared plus 2wh plus 4wh, and we can combine those like terms, 2w squared plus 6wh, which is a good expression for the surface area of our box. Now, this is in terms of 2 variables. We've got a w there and we've got an h in there. Going forward, we know we want to take the derivative, we want to set it equal to 0, and we want to solve for where that minimum occurs. In order to do all of that, we need this to be a function of 1 variable. So we've got to get an expression for either w or h in terms of that other variable. And that's going to come from our volume expression up here, because we can take this and we can rearrange this to solve for h. H is going to be that 2,400 divided by 2w squared, or let's see, 2,400 divided by 2 is just going to be 1,200 divided by w squared. And we're going to take this expression for h and we are going to sub it in down here for h. So our new expression for the surface area is going to become 2w squared plus 6w times 1,200 over w squared. And by doing that, we've changed our equation for the surface area to an equation with a single variable. Now, we can rewrite this a little bit just to make it easier to find the derivative. I can cancel out a w here and here, and I'm going to multiply the 6 times the 1200. So this first term isn't going to change. This is still going to be 2w squared. But if I multiply the 6 by the 1200, I'm going to get 7,200 or 7,200. And instead of having this as 7,200 divided by w, I'm going to write it as w to the negative 1. That's my expression for the surface area that I'm going to optimize. So optimization, we are going to take the derivative. So our surface area squared is going to be, let's see, derivative of 2w squared, we're going to bring down the 2, so that's going to be a 4w. 7,200w to the negative 1, we'll bring down the negative 1, that'll make this negative 7,200. And subtracting 1 from the exponent gives us a negative 2. To find our minimum, we are going to set this equal to 0. So how do I solve something like this? I'm going to start by bringing that negative 7,200 term over to the other side. So I'm going to bring that over as 7,200, and I'm going to change that w to the negative 2, rewriting it as over w squared. I want to gather all of those w's together, so I'm going to cross multiply by w squared to get w cubed. Okay. And then I can divide by 4 on both sides, so this will become w cubed is equal to 7,200 divided by 4, which is 1,800. Okay. So now I can solve for w. W is going to be the cube root of 1,800, which is going to be 12.16. So what were we asked to find in this question? We were asked to find the dimensions that will minimize the amount of cardboard. So one of our dimensions is the width of that box, 12.16. We need our other dimensions. We also need our length and we need our height. So to get our length, we'll remember that our length was just 2 times the width. So that'll be 2 times that 12.16. So that is going to be 24.33. And our height, well, we had come up with an expression for height when we were from our volume equation. It was 1,200 divided by w squared. So we can sub in our value for w. 12.16 squared, and we can work out what h is going to be, 8.12. And those are our 3 dimensions. So just to show that we're done here, we're going to sum up with a concluding statement. We're going to say the box should be, let's see, 12.16. What were our units here? They were centimeters, so 12.16 centimeters by 24.33 centimeters by 8.12 centimeters. And we've answered the question.